All right, today I'm gonna work through in this video, mainly we're gonna focus in on distinguishable permutations and combinations in this video. And I'm just gonna work through these notes. There's lots of examples in these notes and I'll try to highlight key points. For number one, here we're looking at license plates and we have 3 letters followed by 4 numbers. Alright, so we have 3 letters followed by 4 numbers. If we allow for repeats, in my head I already know permutation. Nope, not allowed to use permutation. How many different license plates can be made? And this is already telling me, use the multiplication principle of counting. So for that, I'm going to draw a blank for every stage. 1, 2, I have 3 letters, followed by 1, 2, 3, 4 numbers. I'm going to draw a line to signify that. So my W1, W2, W3, 4, W5, W6, W7. That means my N is 7. I have 7 stages. Okay. So how many options do I have at the first stage? That's going to be one of my letter stages. And if I were Alan, I would say there were 24 letters, but I'm not. There's 26. Well, it's 26 letters in the alphabet. And I'm allowed to repeat. So I have 26 for all of those options. Now I have the digits 0 through 9. These are my number stages. This is actually 10 digits that I can choose from. So I have 10, 10, 10, and 10. I can multiply all of those out. If you multiply those numbers together, you'll get the answer. This should be your answer. 175,760,000, and this is possible license plates. Okay. Let's look at number 2. In how many ways can these letters be arranged if letters cannot be repeated? So because they're not allowed to be repeated, I know I have the choice. I can use, well, before today, I knew I only had the choice to use the permutation formula. I could also use the multiplication principle of counting, but I'm just going to go ahead and move forward with the permutation formula. So one possible arrangement is LUV-AQR. Another possible arrangement is AQR-LUV. The order of the numbers changes the meaning of the word. Okay? They're very different things. And this list would just keep going. So I have the potential to rearrange all 6 letters at the same time. So the permutation formula is n factorial divided by n minus r factorial. My n, or total objects, that I'm rearranging is 6. I have 6 letters. My r, I'm choosing to rearrange all of them, and that's okay. So let me plug it in. 6 factorial divided by 6 minus 6 factorial. 6 factorial divided by 0 factorial. 0 factorial is equal to 1. 0 factorial is equal to 1, so this reduces to 6 factorial. Which is 720 ways. 720 ways. So let's go ahead and look at this example on the next page. Let me just start by talking about the example before we move into the formula. Let's say I have the word moo, and I want to see how many distinguishable ways can they be rearranged. So let me start out, it's telling me to use a tree diagram. So let me use a tree diagram and branch out for each letter, M, O, O. And then if I go to M as my first choice, I can go to O as the next choice. One O or the other O. And if I go to MO, my third choice would be O. My MO, my third choice would be O. If I start out with O, I can go to M or I could go to O. If I go OM, I can go to O. If I do OO, I can go to M. If I start out with O, I can go to O or M. If I go OOM, or I could go OMO. So let me write down my options. I have MOO. I have MOO. OMO. OOM. OOM. Or OMO. So that's 1, 2, 3, 4, 5, 6. But how many of them are actually unique? These two are the same. These two are the same. And these two are the same. So I only, in total, have 3. And I only have 3 ways to rearrange those. So let me think about this in terms of the formula that we've learned, permutation. We're not repeating letters. Okay, so I have N equals 3 because I have 3 letters. R equals 3 because I'm rearranging all 3 of them. So let me plug it into the permutation formula. This reduces to 3 times 2 times 1, which is 6. So I notice that this is the total number of branches that I had, but the answer ended up only being 3. It was only 3. So how can I get this number with a formula? Well, this is how. This is a way that you can get the total number of distinguishable permutations. So here we have N objects that are broken down into different types of objects. So let me look at this in terms of mu. I have 3 total objects, so my N is 3. How many unique objects do I have? K is the total unique. I can't spell. Unique objects. So how many unique letters do I have in that word? 2. I have an M and an O. So I'm going to have an N1 and I'm going to have an N2. I go all the way up to whatever my K is. I'm going to let N1 be M and N2 be O. So how many M's do I have? Well, let me look at my word. I only have 1 M. How many O's do I have? I have 2. So once I'm this far, all I have to do is plug it into the formula. My N is 3, so I'm going to have 3 factorial on top. My N1 is 1, so I'll have 1 factorial. And then I'll have 2 factorial. So this reduces to 3 factorial over 2 factorial, which is 3. So that's how you cut down permutations whenever there's repeating letters. So the key point here letters are repeated. Letters are repeated. So let's look at an example. Use the formula for distinguishable permutation, so it's telling us what formula to use, to determine how many distinguishable ways these letters can be arranged. So I see lots of repeat letters. Let me go through and identify how many of those letters are unique. I have M, I, S, and P. M, I, S, and P, that's 4 unique waves, 4 unique letters. So I'm going to let N1 be my M. How many M's do I have? 1. N2 is going to be my I. How many I's do I have? 1, 2, 3. I have 4. My N3 is going to be my S's. How many S's? 1, 2, 3, 4. And my N4 is my P's. There's only 2. So now I have all my variables ready to plug into the formula. Oh yeah, except for N. N is going to be the total number of letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N should be 11. Actually, all of these add up to give you N. So let me double check that. 1 plus 4 plus 4 plus 2 is 11. Yes, that's a good check. So on top, I'm going to have 11 factorial. And on bottom, I'm going to have each of these factorials multiplied by each other. So 1 factorial times 4 factorial times 4 factorial times 2 factorial. So let me plug that in. You should get, there's 34,650 waves. That's the total number of ways we can rearrange those letters. So let's talk about number 3. All of our dreams have come true. Thanks to a cloning machine, there are now 2 Drakes, 3 Rihannas, but there's only 1 Madonna. So assume these are members of a top secret society, and they're taking their annual holiday photo. And how many distinguishable ways can these performers be arranged in a straight line for the photograph? So this assumes that the clones, we can't tell them apart. So I'm going to break this down into a letter problem like the one we just saw. So if I have 2 Drakes, I have Drake, then Drake. I have 3 Rihannas and 1 Madonna. My N, or total letters, is 1, 2, 3, 4, 5, 6. My N1 is going to be my D's. There's 2. My N2, those are the R's. There's 3. And my N3 is 1 for my M's. So if I plug it into the formula, I have 6 factorial divided by 2 factorial, 3 factorial, and 1 factorial. So this answer, let me go to my calculator. 60 ways. There's 60 ways that they can be arranged. So to recap, permutations. These are ordered arrangements. If we're arranging things and we have multiples, so if multiples, then we need to use the distinguishable permutations. Okay, these are about to get a little bit more complicated. Yes. Now we have permutations, distinguishable permutations, and now we have combinations. These are all the different ways you can denote a combination. N is the total objects. R is the objects chosen. And the total number of combinations that you have is given in this formula here, and R is between 0 and N. So what's different about a combination and a permutation? Well, let's look at this